Hello guys, so welcome back to our VHDL lessons. So we're gonna see another type of, or another style basically, and this is the first time to see it. Another style to code in VHDL, and this style is essentially used for synchronous circuits. You can use it, by the way, for combinational logic, but its main purpose to serve in synchronous design, synchronous circuit design basically. Okay. And that's using the process statement. This is the first time to see this process statement in here. And whenever you have a process and in the process, the lines between these two statements are ordered. I mean, order doesn't matter here. Don't this is not similar to what we discussed in here. We change it the order. You can change the order in any way you want. The result will be the same. Okay. But here, no. Here, the order does matter. You cannot change, the order. Okay. So maybe for that particular design, it's not that important. I mean, you can make this line before 13 or 13 before 14, but in most generally, the order does matter. Okay. So let's check it. This is also this D flip-flop is basically positive edge, not negative edge. And also has a reset input. We explored in the lecture, the reset input. We said that it's really important in synchronous designs, and it really is. And especially in simulations. Okay, and using reset, if you use this signal, then you force the output to be some value, whatever it is, 1 or 0, whatever you like. By the way, it doesn't have to be 0. Okay. Also, usually the concept of reset, when you hear reset, that means make something 0. Okay. But the basic idea is to make the output with some known value based on the designer choice, either 0 or 1. Okay. So this D flip-flop it's a D flip-flop basically, rising edge, not negative edge or positive edge, and it has a reset input. So the input, we're gonna add another input, which is we call reset here. You can call it whatever, but it's a reset input. The clock here, it's also a very important input for any synchronous circuit. And of course, the D input for the flip-flop. And the outputs are the same, Q and Q bar. Okay. So let's see. The process statement must have a label. So you must put a label here. So just call it whatever, call it D. For example, I call it here D flip-flop process, I mean. Okay, but you can call it. And why it should have a label? Because you might have many processes in the same design. Okay. That's a legitimate, way to code. I mean, you may have a process number 1, then just copy and paste. So call this, for example, 2, and this is call it 1. So you have here 2 processes. So this is a legitimate and this is valid, design, but this will result in 2 D flip-flops, not just 1, 2. Okay, that's why the process statement should have a label. So we don't need this. Let's remove it again. So the process needs what's called sensitivity list. Sensitivity. So this clock and reset, let's write them on the side here as a comment. This is basically the sensitivity list of that design. Okay. And what is meant by sensitivity list? It's a list of signals that this process will be executed whenever there is a change in any of them. So that's really important. And that's basically the concept of synchronous circuit, especially with the clock. We said that whenever you have a clock changing from 1 to 0 or 0 to 1, then there will be a change in the output. That's basically the concept of sensitivity list, when there is a change. And generally, you can have some flip-flop or whatever synchronous circuits, it can change in both, clocks, positive and negative. So you will have a change in the negative of cycle, negative edge and the positive edge. This is generally. Usually you use one of them, but you may have both. Okay, for example, when you study the counter in the future, we're gonna see, I will give you an example in which you're gonna count or increment the count basically in the positive edge and also in the negative edge. Okay. So whenever we have a change in the clock or the reset, this code in here between the begin here and the end will be executed. Otherwise, it's not. I mean, if D changes, this will not be executed. Only executed when clock and reset, it changes. Okay. And that's the flip-flop. We said that whenever you have a change in the D, it will not be reflected in the output. It will not be copied in the output unless there is a positive edge or a negative edge based on the designs that you have. Okay. So there is also another statement that we not usually, it must be used within a process, which is the if-else statement or if statement basically. If statement is another cool, feature in VHDL that we use all the time to code or to describe the behavior of synchronous circuits. Okay. So in if statement, you just put a condition, and based on that condition, you're gonna assign something, to the output. So I'm saying we know that whenever there is a reset, when you put a reset is 1, based on the designer choice. You may choose the opposite, that if the reset is 0, you reset the circuit. But here I'm choosing that if the reset is 1, when I assert the reset, then the output will be 0. So I'm saying this: if reset equal to 1, then assign to Q the output port. Where is out? Yeah, Q. Assign to it 0. And of course, the Q bar should be 1. Okay. Then else if rising edge of the clock. So here you are defining that this flip-flop is a rising edge flip-flop or a positive edge flip-flop. Okay. And here is the way you code this rising or negative edge. Okay. So rising edge of the clock. If you want the negative edge, you should write falling edge of the clock. Okay. Then else if the reset is 0, I mean you are not resetting the circuit, so the circuit will do its function. Its function is a D flip-flop, a positive edge D flip-flop. So on the arrival of a positive edge, D should be copied to Q. So Q will be equal to D, and Q bar should be equal to not D. Then in the if and in the process. Any statement in VHDL has an end. Okay. So if, then you have end. The process is a statement. It has a begin and it has an end. Okay. That's basically how you code. And this is behavioral design. This is a behavioral, it's not a structure anymore. And we're gonna see, because of the complexity of synchronous circuits, we're gonna most of the time use behavioral design, something that describes the circuit, that describes its function. Okay. And this coding is really close to the programming that we learned, in our school. I mean, C++, whatever MATLAB, even whatever language you use or you program with before, you will find that process or synchronous coding or behavioral coding is really close to that concept. You have ordering. Order is important. Most of the time, generally, here it's not. You can switch Q bar and Q. I mean, line 14 and line 13 or line 16 and line 17. It will not affect anything. The operation will be the same. But most of the time, no. Most of the time, the order is important. But also here, the order is important in the sequence of the if statement. So I must check first, so the compiler here will check first the reset. So first, I mean, it will not go here to the else. No, it must go to the reset and check the reset value first, then execute these two lines. And of course, at that time, it will not look at this. But if the reset was 0, it will look at, that the else part of the if statement. Okay, good. That's basically, the design in using a process. Let's now check the test bench. Test bench is exactly the same as the one that we tested for the master slave D flip-flop. Exactly the same. Just changed, of course, the naming here to reflect the new design. Okay. Again, same way of generating the clock. Okay. And of course, we have here a new input, which is the reset. That's why here is the reset, I'm also asserting or disasserting it in all, the situations I have here. Okay, so let's run this, start the simulation. We are D flip-flop version 3. Test bench. Of course, it says it doesn't change. We just make comments, so it doesn't matter. That's why I didn't compile again, because I know that the design is still the same. Okay, here is let's run it. Let's zoom out. I have many. Okay, let's check. So let's mark the clock with yellow, just to check where is the positive edge and negative edge in a very easy way. And let's make you and the reset. Let's mark it with blue, for example, or any other color. I don't like to mark colors, use the red color, because red color is usually used by the system here, and the green for the undefined and defined values. So that's why I prefer not to use red, not to confuse myself. Okay, so let's look at the beginning here. So the one big advantage of using reset, you avoid the undefined. Because this undefined, especially with simulation, this undefined states that we see when we tested the master slave D flip-flop, okay, doesn't appear here, because when you have a reset is equal to 1, you resetted the output, so the Q is 0, log the Q is 0, and of course Q bar is 1. Okay, that's basically, and of course, the clock here doesn't change the situation. I mean, here we have a positive edge clock, positive edge at 1.5 nanosecond. Okay, and D is 1, but that doesn't reflect to the output. The output stays 0 because the reset is 1. Okay, here the reset goes back to 0, but it's a negative edge at the clock, so that will not affect the output. The output will remain 0 and doesn't reflect the value of D, which is 1. But here, no. Here we have a positive edge. The reset is 0, so the output copied the input, and the input become 1. Here's we have a change to 0, but it's a negative edge that doesn't change anything. Here we have a positive edge that change, so the output will copy the input, so the output Q will become 0 now, because at 7.5 nanosecond D was 0 when the positive edge arrives, and so on. It will be exactly the same as the previous previous output with the master slave flip-flop. Okay, guys, that's it for the T flip-flop. In the next two videos, we're gonna explore the design for the T and also the JK flip-flop. Thank you very much for watching this video, and see you in the next video. Bye-bye.